We've talked about how solubility can be changed by changing temperature or pressure or things like that in a previous video. But now we need to talk more specifically about solubility and put some numbers and some terms to it. So solubility says whether or not something dissolves. And what we find is that there are three states a solution can be in when things are dissolved in it. Three main states that a solution can be in. So the first one that we're going to talk about is unsaturated. The second one we're going to talk about is a solution can be saturated. And the third one we're going to talk about is a bit more rare and a little more complicated, and it is supersaturated. So a solution can be unsaturated. This means that it can hold more. So if you have some, let's say, tea, and you're trying to make sweet tea, and you want a little more sugar, and you pour more sugar in, and it's able to dissolve, that means your sugar or your sweet tea was unsaturated. So this is a solution that we'll say it can fit, and by fit I mean dissolve, more solute. So if you pour more solute in, it will dissolve, and of course I mean this at its current state. So what do I mean by at its current state? I mean without increasing temperature or changing anything, it could dissolve more solute. If you poured more in, it would dissolve. This is unsaturated. Saturated means it cannot fit any more solute at its current state. So if you're trying to make sweet tea or Kool-Aid or something like that, you will get to a point where you're stirring and the sugar just won't dissolve anymore. That means it is now saturated at that point. When it's saturated, the only ways that we could get more to dissolve is by changing its state. So we could increase the temperature, now more would dissolve. But at that current state, it is saturated. Or, of course, we could pour more water in, because more water would allow this to occur. All right, so that is something that we can do. Now, supersaturated. What does supersaturated mean? Supersaturated means that there is more dissolved than can dissolve at its current state. Now, this seems like a very contradictory statement. How could there be more dissolved than can dissolve at its current state? Well, what this actually means is if you poured in sugar or poured in some solute at its current state, at a certain point, no more would dissolve. However, if you increased the heat, if you heated it up, you could dissolve more. But then you could cool it back down, and the sugar wouldn't necessarily precipitate right away. So that means that we dissolved it at a different state, but then we changed its state, and now there's still more dissolved than could dissolve at its current state. So the way that we make this work, and actually these are very unstable solutions, and it's really interesting what you can see happen. Sometimes if you drop one little crystal in, into this, because it's so unstable and volatile, you'll just see a huge precipitation occur. So this is a really interesting state and one of my favorite to do experiments with and to look at. You can see the crystals begin to grow off of the seed crystals that were dropped in. These seed crystals are the same material that is growing, but the supersaturation creates a situation where the crystals spread out and grow from this point because they are not soluble. Now, we need to look at a graph and kind of put some numbers to this. So this is a common solubility graph right here, and they're really interesting because what they do is they put temperature on the bottom. So as you go to the right here, you are actually increasing the temperature. And then over here, on the y-axis, we actually have grams of solute per 100 grams of H2O. So essentially what that means is a number like this one right here, 60, means that there are 60 grams of solute dissolved in 100 grams of H2O. Now, just to kind of foreshadow something, what does this right here mean that gets kind of confusing? How many grams of total solution do we have? Well, this means we actually have 160 grams of solution in this case, because this on the bottom is 100 grams of H2O, not 100 grams of total solution. So let's do some problems and kind of look at this. But first of all, before we get too far into it, I want to look at some of these and how they change with temperature, because they're not all the same. So NaCl, table salt, we see right here. If you heat something up, will it fit more table salt? Well, let's look. Can you guys trace NaCl right here? Yeah. There's NaCl. And yes, it will fit slightly more as we increase the temperature, but as you notice, the slope isn't very steep. So this really, as you increase temperature, doesn't change much in its solubility. So looking at table salt, what would everything down here be? Everything below this line. This would all be called unsaturated, right? If we have, let's say, 20 grams, say it's at 50 degrees Celsius, and we dissolve 20 grams of salt in the solution, we would be right here, right? Can you guys see that right there? So we would be able to still dissolve quite a bit more to reach up here where it's saturated. So this point right here, the actual line, this actual graphed line right here is saturated, right? And then everything up here, everything above the line would all be super saturated. So if you get more dissolved than the line shows, it would then definitely be super saturated. And that's how we can read these graphs in general. So we've looked at salt, but let's look table salt, but let's look at some more of these that could be pretty interesting and pretty important to look at. So what about potassium nitrate? Potassium nitrate is a fascinating one, KNO3 right here, because as you can see, as we increase the temperature, potassium nitrate has a huge increase in its solubility, right? And we see it just keeps climbing here, and it's crazy how much soluble. So if you look and you read the graph, you realize that here at 70 degrees Celsius, we see 70 degrees Celsius right here. If we follow the line up at 70 degrees Celsius, how much could you dissolve? You could dissolve probably like 128 grams of potassium nitrate in 100 grams of water. So that means that actually you can dissolve more potassium nitrate than water in water. And this is where it gets really interesting, because technically, if we follow our old definitions of solute and solvent, now the potassium nitrate in a way would be, our solvent, but we kind of ignore that because that's a weird definition. So that is the basic example of potassium nitrate. So let's keep looking at another one that I think is pretty weird and pretty interesting here. Ammonia, NH3. So if we look at ammonia right here, we notice that ammonia, as we increase the temperature, actually decreases its solubility, as we can see. And it kind of tapers off here as we get further over. So ammonia is also a really weird one. And there's a bunch of other salts here, as we can see, that also cesium sulfate on the bottom here also would decrease its temperature. So another kind of weird one. So now that we have kind of looked and we realize that on the line is saturated, we can calculate a lot of really interesting things. So let's try a problem, the kind of problem that you might expect to see from one of these questions. So a chemist is making a solution of saturated, that's an important word right there, right? Saturated. So we know what that, we already kind of are starting to see what that means. Sodium chloride at, let's say here, 80 degrees. We're going to go with 80 degrees. So he's making a saturated sodium chloride solution at 80 degrees. You know what? Let's make it easier. Let's make it 90 degrees, because then we'll be right on the line here and it'll be easier. At 90 degrees Celsius. If he wants to make 100 grams of solution, how much NaCl should he use? Now, this is a tricky question because many times people read a question like this and they just want to read the graph right away and say, hey, 90 degrees Celsius, look, it crosses the line at 40. And hey, remember, this is per 100 grams and he wants to make 100 grams. So wonderful. Let's just call it good and say the answer is 40 grams. Now, that's not correct because the problem is this is 100 grams. Remember, 100 grams of solution. And if we go back over here, we remember that this here had 160 grams of solution because the solution is both the solute and water, the solvent. So how are we going to solve these questions? Well, the method we like to use is a proportion. So let's look at the information we know right away. We know that at 90 degrees, at 90 degrees Celsius, 40 grams of NaCl will dissolve in 100 grams of H2O, right? So we know that. And then we are going to set that equal to our products over here. And this is going to be our actual situation that we're looking at in this problem. So what are we actually looking at in this problem? Well, he wants to make 100 grams of solution. So we know that we have some solute and some solvent here, and I'll just call them X, which is going to be our solute, and I'll even use the proper colors here. X, which is going to be our solute, and Y, which is going to be our solvent. Now, I'm going to get rid of these really quickly, but I just want to use the algebra to show you how this works. We know that X is our solute and Y is our solvent, and we know that solute plus solvent gives our total solution, right? We know solvent plus solute gives us is the total solution. Those are the two parts to the solution, right? So we know that X plus Y here, which is our solvent, is going to be equal to 100 grams of total solution, right? So what we can do in this case is solve for one of them, and I am going to choose to solve here for solvent. I like to solve for solvent. It just makes sense in the end to me, so I'm going to subtract X on both sides. We have Y is equal to Y, which is our solvent, our amount of solvent is equal to 100 grams minus X, which is our solute. Now this is really nice because we can use our substitution method, which means Y, since Y here is the same as this Y here, that means I can substitute everything right here in these parentheses in for Y. So that means really our solvent is 100 grams, or our total solution, minus whatever of it is our solute. Right, and this makes sense because whatever our total solution is minus whatever our solute is going to give us what our solvent is. So that is what we end up getting. Now, just to help you guys out, because you may not want to do the substitution method and this every time, I'll tell you it's always going to be the same. It will always be on top when we set up these proportions. On top, you can always have your solute, and on the bottom, you can always have your total solution minus your solute. Now be very careful here, because since we substituted, these are in parentheses. That's one thing that's very important, because otherwise you're going to make an algebra mistake, right? But you can always just set it up this way. Whatever your solution is minus your solute is on the bottom, because that represents your solvent, right? This represents your solvent in total, right? So this is what we can do to solve these problems. Now, how are we going to actually solve the algebra here? Well, we are going to cross multiply. So you're going to have 40 grams times 100 grams minus X. And that's going to be equal to, on the other side, 100 grams times X. So what we're going to do is distribute our 40 grams in here. And I'm just going to change colors to make it simple for us. So what would be 40 times 100? We would get 4,000 grams minus 40 grams X is equal to 100 grams X. Now we can combine like terms by adding the 40 grams X on both sides. That gets rid of these two. And we have 4,000 grams is equal to 140 grams X. All right. And now we can divide on both sides by 140. to get x by itself. All right, so when we do this, we're going to get 4,000 divided by 140, which is 28.6, about 28.57, but we're going to go 28.6. Is equal to x. So what we're saying is 28.6 grams of NaCl, right? Because remember, x was NaCl, so 28.6 grams of NaCl is how much he should use. So how much water does that mean that he should use? Well, if you wanted to know the water, remember, again, we would just take 100 grams of solution, subtract whatever of it is the NaCl, and we would get the water, which in this case is 71.4. Right? And these two would give us how much salt and water, and that would, of course, total to 100 grams. So that is how we do these sort of questions. Now, they can be easier at times. For example, if you were given the amount of water. So let's try another one that's a little easier. So let's say a question asks you something like this. If you are given a solution that has 50 grams of water, how much, and let's do ammonia, NH3, can you dissolve in it at 70 degrees Celsius? Right? So you have a solution that you're given the water. If you're given the amount of water instead of the amount of solution, it's a lot easier because this right here is our solvent. And remember, our term on the y-axis here is per 100 grams of solute, right? So let's refresh our memory. What was the temperature here? It was 70 degrees Celsius, right? So let's find 70 degrees Celsius here, all right? And at 70 degrees Celsius, if we follow it up, we see the ammonia line is right here. So we follow the y-axis over, and it looks like we're right at about 15 grams. We're very right balanced there at about 15 grams. Actually, my line may have sloped down slightly, so it's probably more like, if we really follow it well, it's probably closer to 16 or 17 grams. So we do the best we can reading these. So what we're saying is 17 grams of ammonia can be dissolved at that temperature in 100 grams of water. Where'd I get the 100 grams? Remember, that's what the y-axis says. The y-axis gives us the number in grams. So that is equal to whatever we have here. Our question is, how many grams of NH3 can we dissolve? And on the bottom, we would put 50 grams of water because that's what we are being asked for, right? That's from the question. So remember, whenever we do these problems, we're always going to have two sides. We're going to have this side that's from the chart or from the graph of knowns, and we're using a proportion to set that up proportionally to the question, so from data, the question we're given, right? And in this case, we're going to solve for the grams of ammonia. So how are we going to do that? Yet again, we cross multiply, but it's a bit easier this time because we don't have subtraction or any parentheses here. So all we get is just a quick and simple 17 grams times 50 grams. And then on the other side of our equality, we have X, which we are looking for grams of ammonia, times 100 grams. These are multiplied, right? So that means the simple solution is divide by 100 on both sides, and we're already going to be done this quickly, right? Because those two cancel right there. And so all we need to do is 17 times 50 divided by 100, and we get 8.5 grams of ammonia would be able to be dissolved in that. And that is a bit of an easier problem. So these are the ways that we can do these problems. Always remember you're setting up a proportion, one side the graph, the other side the data from the question, and always be very careful and pay attention to, is it giving you grams of water or solvent, or is it giving you the actual grams of the entire solution, right? So that's pretty important, and these are for liquids. Now, it gets a little more complicated when we get into gases, but we won't worry about gases too much in this class. Just remember that if we increase the pressure of a gas, it will increase its solubility. And if we increase the temperature of a gas, this is just a quick note. We've already talked about this in a previous video. If we increase the temperature for a gas, it's always in a gas going to decrease solubility, right? Whereas if we increase the temperature in a solid, it's usually going to increase solubility. As we've seen here though, things like ammonia, it doesn't if we look at this graph. But the majority of them, if we really look through all these, the majority of them are all going up, as we can see here, the vast majority.